Good day, everyone. My name is Kotatso Mahuma, and I will be covering the software development source files section. Just to give a brief explanation, this project is Brownfields development, where the goal is to modify and enhance an existing code base. Based on the requirements given in our curriculum, we had to refactor robot worlds and add new functionalities that would enable the game to be used in the real world. But before starting, we first cloned the project file onto our devices and used either IntelliJ or VS Code to work on the code. Here's a demonstration on how we cloned our file. We used the command git clone and pasted the SSH key so that it loads on our devices. Once it's done loading, we just confirm that our project file was loaded successfully on our desktop and ensure that all the files needed to edit the file was present. So Git was the tool that we used as it enabled us to work together smoothly without overriding each other's work. In this demonstration, I used the command git version to check the version that I am using. And to ensure that the code base I have on my personal computer aligns with the code base on GitHub, I use the command git pull to update my code base. And as you can see in the demonstration, 36 files were changed, meaning that my file has been updated to align with the file on GitHub. I'm also able to track the number of commits using the git command git log, which enables me to revert back if needs be. In accordance to the requirements on the curriculum, our project had to consist of the POM XML file, the database file, a make file, and a web API file. We utilized the majority of the functions in GitLab to keep track of our commits, ensure continuous workflow, consistency, and accountability in our group. First, we used the issue boards to structure our stories and categorized it by using backlog, in testing, ready for development, in development, ready for showcase, and done labels. Also listing each story based on the priority. We also wrote a wiki file to give a brief summary of the project and its requirements, broke it down simply and neatly into iterations, stated the user requirements, added a makefile command, and a web API command for easy access. We are also able to track our repository and see that we do get updates based on the commits. And we are also able to track each individual person who committed. This is also for reverting purposes. And we also used GitLab pipelines to ensure continuous integration and continuous deployment for our project, which aided in automating processes such as testing. So we were able to test our code, and we drew pipelines from when it was in testing, in development, and our goal was to reach a successful deployment. We also used the analytics to track our progress, Our CI/CD analytics prove and show that our pipeline have been functional and show that we do meet the requirements for continuous integration and continuous deployment.
Hello everyone, my name is Annelisa Mhlamo and I'll be covering code and design conformance, which is how our code and design align with the standards outlined in the curriculum. To begin, let's look at the structure of communication protocol. That is the way the client side communicates with the server, as well as how the server communicates with the client side. So the client sends request messages to the server and receives response messages. Every request is replied to. It can be an error response or a successful response, but result of trying to execute a command must always be presented. Both the request and the response is a JSON string with the structure as shown. To ensure that we conform to this protocol, we made a request class to handle the request and response classes which extend from this abstract class. They handle error responses as well as successful responses. Let us take a closer look at our request class, which is responsible to create and manage requests for commanding a robot. It serializes the requests into JSON format for communication with the robot or a server. And we use JSON for the conversion to JSON. I'm gonna just take you through some of our methods and constructors. We have a constructor there that is responsible to initialize a robot name and a command, because sometimes it's just the robot name and a command. We also have a constructor that is responsible to initialize the robot name, the command, and the arguments. Because sometimes it's the robot name, the command, and an argument that goes with the commands. And just going down, we have a method, launch robot, which is responsible to set the robot name and command and converts the request object to a JSON string using JSON, as well as a command, as well as another method that is responsible to set the robot name, command, and arguments, and converts them to a request object, and to that's going to be a JSON string using JSON. Now, let's look at our error response class, which is responsible to handle requests that, for an example, are not supported by the server, or if there is an internal error. The idea is that the server must always respond to a command no matter what happens. So this class is able to set results to error and the data field to a map containing a single key value pair, with key being the message and the provided error message. And now our successful response clause. So when the request is successful, it sets the results to OK and sets the data of the robot using JSON objects, as well as the state of the robot using state JSON object, as shown there in the class. To showcase live what I've already covered, there I launch a robot Blaze with the name Alyssa. And as you can see there, after the launch was successful, the results are set to OK. The position of the robot is stated, as well as the direction, shield, shot, and status. And now let's say I want to move forward, and I say forward 10. The results are okay because that was a successful request. So the message and the position, the direction, which is the state of the robot, is also indicated in there. So if I put nothing there, the results are error, message, unsupported comment because I put nothing. And also on our server side, um, the protocol is observed because the results on when I launched the first command when I launched, the return response was okay. The results were okay because that was a successful response, as well as when I moved forward, when I moved the robot forward, the results were okay, and the when I inputted nothing in there, the results were error because that was an error. So that is also shown on the server side. Uh, Moving along, to ensure that our application is able to connect to the SQLite database and that all the connection is managed, we used JDBC connection source from ORM Lite to establish the connection as shown in the class. So this code includes a method, populate tables method, to ensure that necessary tables for world and obstacles exist in the database. And if they don't exist, the method creates them using ORM Lite's table utils. It also includes a method that is responsible for saving the current state of the world under a given name. To ensure that the world data is retrieved as JSON, there is a method to retrieves the stored world information and converts it into a JSON structure using JSON's object mapper. This is useful for any functionality that requires world data to be output or processed in JSON format. A detailed map of the world, including all obstacles, which is essential for returning comprehensive world data, is built by a special method, prepare world info map. So, in conclusion, the ORM connection class serves as the backbone of database interaction in our system, handling everything from establishing connections to saving and retrieving world data efficiently. To ensure that we have a successful working software product that corresponds with the requirements, we included tests, unit test and acceptance test. So unit test verify individual units of our code. Methods are tested, also single lines of code. So accepting testing, which test against our reference server and live server, test correct functionality as expected by clients, users, or other stakeholders. So acceptance test combine a combination of integration test and user interface test. We use JUnit testing framework. To run our unit test, we use the command line with the command make run unit test only. And there is our unit test running. So that's all our unit testing there. And to run our and to run our acceptance test, we use the make test protocol command as already shown. And there is all our acceptance tests. For user installation instructions, we included a README file, which includes the purpose and the outline of the project and the setup on how you can set up and start the server, as well as how you can package the server to be executable, as well as how you can pull the Docker container, how to log in and to actually run the Docker container. We also include how the client can start to, how they can start the game. We also include commands or instructions on how you can actually play the game, such as how you can launch a robot and how you can engage with the game and how to like explore the world. And um, we included also the game rules as well as test execution. We have we just elaborated on the fact that we have separated our test to ensure ease and use of clear outcomes. So there you can see that you can be able to run the unit tests and protocol acceptance test as well as database acceptance tests. Now, let's look at our project outline. Um, this is a standard format for a Java project managed by Maven. So we have the layout there that includes packages, that include the respective classes. In our source, we have the main application code and tests. We also have on our project directory, we have our files, which is the YMA file that is responsible for configuring the GitLab pipeline. We have the JSON file for world configurations. We have the Docker file. We have the make file that makes the recipes for our project. We also have the POM file for Maven configurations, as well as the README file that I just showed previously. It's the one that contains all our project information. Um, Now I'm going to hand over to the next speaker. Thank you.
Good day, my name is Justin Farrow. I'm with Group 8 of the Cape Town cohort, and today I'll be discussing our research and implementation of database management systems, as well as evaluating the use of SQL and database management in the context of a web application. Before we get into our specific implementation of database management, it's always good to understand what the issue is that we're solving. And anytime you're trying to persist data, you're of course going to face certain challenges. Some of those challenges include data consistency, data redundancy, race conditions, and data security. Data consistency is ensuring that your data always remains the same value unless you're intentionally changing it. Data redundancy is that you're only storing one copy of the data that you'd like to persist, because if you're storing multiple copies and you change the value of one, then you basically have two things that are meant to be the same but are no longer the same. So it's always best to keep one copy. Race conditions is when you have two people that are trying to alter or get the data at the same time. And of course, if one person's altered the data while someone is getting that data at the exact same time, you need to handle that correctly, because you could have it that the data has now been altered, but someone still has the old version of it. And then another challenge is data security. So you want to ensure that the people that are able to access your data have authorization. They are the people that should be able to have access to your data. And yeah, so in order to solve some of these problems over the years, we have seen the rise of database management systems, and they have certain features that are able to basically ensure that those challenges are covered, that they aren't an issue as much as they could be. So some of the features of database management systems are transaction management, data normalization, and access controls. Transaction management is essentially a way of interfacing with your database that prevents operations on that database that shouldn't be happening. So transaction management, in most cases, can help you resolve the challenges of data consistency and race conditions by ensuring that the way that your data is being manipulated is done in a structured way. And then there is data normalization, which essentially ensures that when you store something to your database, it's only stored once and it is stored correctly, which helps with data redundancy. And of course, your DBMS should have some form of access control, which is either if you use your DBMS in an application, you ensure that people that are able to log into that application are authorized users. Over the years, different DBMSs have been developed to solve different kinds of issues, and some of these DBMS types are relational databases, NoSQL databases, and hierarchical databases. So relational databases tend to take the structure of tables with rows and columns, and they enforce a strict schema with defined relationships. Some examples of relational databases are MySQL and PostgreSQL. And a use case would be something like a banking or financial system where you need to maintain strict relationships between sets of data. Our next kind of database is a NoSQL database. Their structures can vary, but some common ones would be something like a key value pairing. Their schema tends to be a lot more flexible than relational databases, an example of which would be MongoDB or Redis. And a very good example of NoSQL is something like a social media platform where your data, since you want to store it all together, but it does not necessarily have a clearly defined relationship between it all, you'd want to use a NoSQL database. And our last main type of database is a hierarchical database, which takes the structure of a sort of tree with parent-child relationships, and the schema is very fixed in that hierarchy. An example of which would be IBM's IMS, and you'd want to use this for anything that has a child-parent relationship, something like an organizational chart or a file structure. And with these DBMSs, they often have various kinds of end-user tools. Some examples would be query builders, reporting tools, and data visualization. So a query builder would assist someone to query the database without necessarily having to understand its schema or even SQL, which can be very helpful for someone that maybe isn't so technically inclined, but it can also be quite limiting in the sense that if certain queries haven't been inbuilt into the query builder, you wouldn't be able to access that data. And with reporting tools, that is basically something like a dashboard where you would be able to see at a glance the state of your database. But of course, if that hasn't been set up to look at certain data, you might be missing out on something critical. And then there are data visualization tools. Much like reporting tools, it would give you at a glance status of your database. And it has the same drawbacks where if it hasn't specifically been set up to look for certain relationships, you might miss them. So here we have an example of what the client would see when interfacing with our database. So on the left, we have client interaction. On the right, we have an SQLite instance just to show what the data would look like once it's been persisted. So a requirement for accessing our database is that you have a running server instance as seen on the left. And the reason we've done this is because the server is what is responsible for maintaining the world and its state and which obstacles are attached to it. Some of the objectives that we had when developing our database would be that the user would very easily be able to interact with the database without necessarily having to understand SQL or really anything about databasing. So if they wanted to save a map, they simply need to type in save into the server terminal, and that would prompt them for a name. And once they hit enter, the world will be saved underneath that name. And then if they would like to restore it at a later point, they would simply say restore and the name of that map. And then that would now bring the persisted map into the server and create a live instance of it. Some of the major performance factors that we developed with in mind are that we wanted the interactions to happen as fast as possible. From our own polling, it takes about half a second on both save and restore to add data to the database as well as retrieve it. And of course, we wanted it to be as simple as possible to use. So we felt that the best way to do that would just be to prompt the client for, to prompt the user for what they wanted to do. So just simple text interaction, and all the SQL and stuff is hidden from view. And the user requirements that we developed this in mind with is that the user should be able to save a map and all of its obstacles and be able to restore it at a later date. Here we have our database schema. So this contains tables, maps, and obstacles. In our maps table, we have columns name, which is the primary key of that map, and it is simply a string. It's a word. And then alongside that, we have a size column, which is the size of the world. In our obstacles table, we have columns ID, which is the primary key for obstacles. This is auto-generated and assigned by the database when the obstacle is saved. So it's simply an integer that rolls forward. And alongside that, we have type column, which is the type of the obstacle, the size of the obstacle, its starting X and starting Y, and then the world ID. The world ID in this case is a foreign key, and it's a relation back to the map that the obstacles were saved with. And in this way, we're able to link our maps to the obstacles that it was saved with. This establishes a one-to-many relationship between maps and obstacles, as we can have one map and many obstacles, but we cannot have an obstacle without a map. It must have its world ID as a foreign key. Our tables do conform to the third normal factor in the sense that when we save the information for an obstacle, all of the information saved at that point relates to the ID that is generated for obstacles, and it's the same case for maps. And of course, when maps is saved to the database, it's saved alongside its obstacles, and since maps has a unique primary key, we are always able to maintain a relationship between the map and the obstacles it was saved alongside with. So here we have a short code snippet on some of the code that we are using to interface with our database. In terms of the tech stack that we went with for database interfacing, we at the base layer went with SQLite. This allows you to store your database as a simple file alongside your code. And this choice was motivated mainly because it was the agreed upon sign requirement that came with our curriculum, as well as it being small and simple enough for the scope of our project. In order to make a connection between our application and that database, we went with JDBC. This is a package that comes with, well, that you import with Java that allows you to make connections from your Java application and your database, and it minimizes a lot of the errors that can come along with making connections to databases. And then further than that, we have used ORM Lite. This is a way to interface with your database in a very error-proof way. So instead of directly managing SQL, you set up something called a data object, and this defines what your tables look like and what the columns in your tables look like. And when you query the database for specific kinds of data, it will be returned in this data object that you can use in an object-oriented way to extract the data and use it as needed. Moving on to evaluating SQL implementation and data management in web applications, we will begin by speaking about our data objects. They have been critical to our use of SQL. As you can see, we have two data objects. We have one for maps and one for obstacles. And using annotations, we let the code know which tables these objects belong to and their fields. And then using their constructors, we can pass our world into the world object and our obstacles into the obstacle object, and it will extract the information from those objects and create data objects if we need to save. And then we also have empty constructors for ORM Lite to generate these objects once it pulls the data from the database. We feel that while this might not be traditional SQL and it is executed as SQL, it does make SQL an easier thing to understand, as you can just see it as a collection of variables rather than this long string. And of course, it will also optimize our queries because we don't have to worry about the actual implementation of our SQL. We use these objects basically to create tables and to query the database. And here we have some of the methods that we're using to execute some of our SQL statements. So again, while ORM Lite does not have us write the SQL ourselves, we have included them as comments, just as an example of what these queries could look like. So for saving the world, you can see when we want to save the map itself, we insert into map the name of the map, which was received from the user when they typed it into the server terminal, and then the size of the map, which we get from our own code, depending on how it was configured. And then for the obstacles, it's much the same. We insert into obstacles all the variables associated with our with that particular obstacle. and that's done for each of the obstacles that were in our world. And then for restoring the world, we actually only make one SQL query, and we can get away with that because we use an inner join. So basically, when we query for the map, already knowing the map's name, we can join the obstacles table onto the maps table. And by having the name of the map, we can get the obstacles because they store the name of the map as world ID within their schema. So using that inner join, we can make one query, and from that we get a world data object. And in that world data object, there's a thing called a foreign collection, which has all of the obstacle data objects included in it. So alongside our database and JDBC and ORM Lite, we've also implemented a web API. So this web API basically handles all of the querying. Instead of our server doing it itself, it has to send these queries to the web API in the form of an HTTP request. And then once the web API receives that HTTP request, it handles accessing the database and returning what it finds as JSON. So the reason that we decided to implement a web API and have it do this is because the web API naturally queues requests. So even though our server could be accessed by multiple clients, when they make these SQL requests, the web API is going to queue them. They can't be executed at the same time. And this basically ensures that we prevent race conditions and that data retrieval is as safe as possible. And also the nice thing about having the web API be based on HTTP routes is that should we make a web application, which was not in the scope of our project just yet, but should we in the future make a web application, it would very easily integrate into this project as it could make HTTP requests and get the JSON itself to use as needed. On our next page, we have a quick example to show that once a map has been saved from our server, that it doesn't actually, we don't have to use our application to get that data from the database because the web API is facing, out on a port, so we can use a simple curl request to get that JSON as seen in the short little video. And just a brief explanation on the flow of data. Basically, the end user would make a request to the web API, and that request gets passed on after it's been processed. And once the web API figures out exactly what the request wants, we query our SQLite DB using JDBC and ORM Lite, and then our SQLite DB will, after that query, of course, get the necessary information and create data objects using ORM Lite. And that ORM Lite data object gets sent to our web API, which will convert what was found into JSON and send it back to the end user. So the end user could be our server, it could be a web application, or as in our example, just a curl request. And we feel that this is a good flow of information because it separates concerns. And at each of the steps, there's different kinds of error handling. So rather than having one big class where, if something fails in that class, there's no moving forward from that. We can catch errors all along the way. And at each stage, the data can be verified and manipulated if needed. Thank you for your attention as we went through some of our database management strategies and our use of SQL. I'll be passing it over to Rudolph, and he will bring you up to speed on some of our testing strategies.
Good day. My name is Tumsani, and I'll be taking you through evaluating test execution and database verification in software testing. This is a key part of ensuring our robot world's game is robust, stable, and meets the required standards. Okay, let's begin. We approach testing through a structured plan, starting with requirement analysis, then creating tests, a test plan creation, creating a plan for the tests, followed by test case creation. From there, we executed the test, logged defects, and finally fixed and re-verified any issues. So we implemented our tests using JUnits within IntelliJ and VS Code. Our tests cover various components, including our database. For instance, our database unit test initially struggled due to the heavy input-output handling. However, by running them through our makefile, they execute successfully. The makefile orchestrates the test environment, making sure the dependencies and setup are handled correctly. Earlier in the presentation, the acceptance and database tests were ran through the makefile, so for reference, please see that. But for now, I'll continue to save time. So here I have for you our launch stories for acceptance tests. So as you can see, we have four different stories, but for now, I'll just be quick and just talk about two. So this is what we use to create our tests. For example, this story it says, as a player, I want to launch my robot in the robot world. So the child items, these are the four cases we had to make sure that our launch succeeds in all these four things. So this is the test plan alignment, how it aligns with our test plan that I just showed you now. So requirement analysis, this user story addresses the need for a robot game to be successfully launched. So test creation, plan and test case creation. The test was created to validate the server correctly handles launch requests and initializes the robot at position 00. Sorry for not mentioning, but we are on 1A. Launch command succeeds. For test case execution, the acceptance test sends a valid launch request and verifies the service response, ensuring the robot state and position are returned. For defect logging and fixes, what will happen is if this test failed, for an example, wrong position, there's no state, or maybe the robot wasn't launched, the defects would be logged for misbehavior in the service launch handling. Fixes would be applied to ensure that the response includes both position and the state. Now we move on to 1B, launch incorrect launch command. So this aligns with our test plan because now for the requirement analysis, the first step in our test plan, the story focuses on ensuring that invalid commands are rejected appropriately. This test was designed to validate that a misspelled launch command returns an error response. That's the test creation plan and test case creation. To validate that a misspelled launch command returns an error. Now for our test case execution, the test simulates an incorrect launch request and checks that the response includes an error message along with the correct error message. Example, unsupported command. Here we logged our defects and made our fixes in terms of should this test fail by not returning an appropriate error response. A defect would be logged related to command validation, command handling, prompting updates to the command parsing logic, basically saying, please enter a proper command, please launch your robot like this. And now I will demonstrate some unit tests. So as you can see, we have a lot of unit tests and we are running them at the moment. It's loading, some are already passing, that's good. So we have roughly around, I don't know why it says 190. We have roughly around 150 something, 160 something tests. But let me just wait. Let me just wait for all the tests to finish so I can proceed with the analysis. So the tests are passing is good, means our program is functioning according to the standards we set. Okay, done. Done. We have 136 tests out of 154 passing. So all of our tests are actually passing because, as you've seen from the makefile, um, all of our tests pass. It's only here that the acceptance tests don't pass and the database doesn't pass. But I've already no, I haven't mentioned that, but I'm gonna mention it. I'm gonna mention it like ahead. I'm gonna explain why that is. But for now, we have 136 tests, and that is very good. Most of our tests are passing. So, moving on to the next. Wait, before I do that, I would like to show you. I would like to show you guys an example of one of the tests, which is the robot test. Yes, the robot test. I'd like to make an example using the robot test. So as you can see, before each test and after, before each test, we set up the robot, making sure it has a state and everything. This is the robot test before we set up the robot. Now for the test, we basically testing every method that we have in our robot class. So test shields, test get shots, test is valid. All those things are being tested for are present in the robot class. I'm gonna show you that just now. Um, Still opening. But yeah, all the methods we are testing for are present in the robot class, and it's actually great that they're all passing, meaning our code is conforming to what we want from it. Okay, to move on, now I'm going to be talking about acceptance and database tests. As you can see on our terminal, I'm running a server. Um, Okay, so now our acceptance test validates the entire system and are dependent on the server being active. So they only pass when the server is running, ensuring that we are testing real world scenarios, the scenarios that we want, the perfect scenarios for our game. This helps us verify that the system functions as expected from the player's perspective. So now I'm running database tests. As you can see, they let me see. They still they're still running. Okay, for our database testing, SQL queries were crucial in identifying and eliminating issues like incorrect queries and performance bottlenecks. By integrating these tests into our makefile, we ensure that they run smoothly as part of our continuous testing process. So as you can see now, it's still loading, but you're gonna see it soon. So now I'm running the database test to show you that they actually passing. And look at this, they actually pass. Great. So moving on, we had a similar issue with the acceptance tests. They only pass when we're running our makefile. They do pass against the server, but I don't have my PC at the moment. But from the test here, you can see our database tests are passing. So I'll move on now. I'll move on now to results and improvements. So as you've seen, we have made around 150, 160 tests, and our coverage isn't great, but it's also not bad either. I would like to estimate maybe roughly 60-70% of the whole project has tests made for it. All the results are logged and reviewed. Whenever discrepancies appear between the expected and actual outcomes, we investigate the root cause, whether it's environmental or just a bug. These reviews have helped us improve our test coverage and focus on critical issues, like here and there where our tests are breaking. This overall has helped our project to be proper, concise, and work according to how we want it to work. And we were able to fix each and every problem, each and every bug that we had. So the whole project, even though it was a Brownfields project, we were following TDD, the test-driven development of creating tests first and then running our program according to what we are expecting from the tests. So that's how reading code expects us to write these programs. Thank you very much. I'll let the other speaker continue. Thanks. Cheers.
Good morning, guys. My name is Kalela Boy, and I will be showcasing the documentation on our project. When we were developing our documentation, we focused on the three components, which are software requirements, documentation, technical documentation, and the end user documentation. Our project documentation followed the structure of a wiki format designed to provide clear consistency information about the design, implementation, and maintenance of each component. By using this standard format, we ensure all the features, commands, testing procedures are well documented and easy to navigate. This approach keeps our documentation up to date with the latest project changes and aligned with the agreed upon documentation plan, making it easy for developers to find and understand the key information. We use a wiki format for all our project documentation. This helps to ensure consistency structure, providing clear information and design, implementation, and maintenance. Each article of wiki follows a standard template that includes sections like overview components, design with diagram and description, implementation details, API documentation and usage examples, testing procedures, and scenarios as well. Each wiki article is consistently organized with a clear title, introduction, and design breakdown, implementation details, usage of instructions, and testing documentations. For example, an article of a reload explain its purpose, interaction with other components, code details, and testing. The documentation is always up to date with the current state of the project. When code changes, related documentation is reviewed and updated in a real time, ensuring that the wiki reflect the latest version of the code. New features like repair command get their own wiki page and are integrated with the relevant articles. Structure and effective. Our documentation is a structure using a tool. We structured our documentation using tools like Miro and Wiki, making it easy to navigate and understand. Articles are linked together with the hierarchical format, ensuring user can find a related information easily. This approach helps developers both new This approach helps developers, both new and experienced, quickly find their way, improving productive and onboarding. For the conclusion, our documentation follow a predefined wiki format, stays up to date and aligned with the original documentation plan. By using a Miro and well-structured wiki, we ensure that our design and code are well documented for each reference.